Hello, it's me again, Rick Morgan, your comic book scientist. You poor suckers asked for it, so now you're going to get some more technical stuff. I'm going to start by talking about paper and what it is and how it ages just naturally, the very basic thing that happens to paper. Later on, we'll talk about desizing, and we'll talk about ink stains, we'll talk about foxing, we'll talk about anything else we want to do, lamination, which you might call pressing of paper. But we're going to start with what it is. And this video is just going to talk about regular old aging process of paper, and then we're going to talk in future videos about the effect of light, the effect of temperature, the effect of oxygen, things that can happen to it normally, and sort of establish what a problem it is and why we want to solve it. And this is part one. Hopefully it's not too long. Oh, and I have a video too. We're going to talk about some Golden Age books. So I'm trying to find some more old Golden Age books to work on. So this one is what I've been trying to get the color out of the back of it. You can see I've had some success here. It used to be all pretty brown and yucky. But anyway, we'll have a video about that as well. But this, for frame of reference, we're working on Six Gun Heroes, 10-cent book from I think 1956 or 7. Anyway, I hope you enjoy the video. Take care. Bye-bye. So, despite the current uncertainty of the U.S. economy, the Overstreet Price Guide and a lot of other indicators show that comic books are actually really valuable right now. And in fact, I myself have spent many tens of thousands of dollars just this year in comic book purchases. So, one of the things that comic books rely on most heavily for their value is, of course, their condition. Their condition is, whether or not the ink is bright and shiny, whether or not there are marks or tears in the page, and of course there's the paper. The paper is we do color by paper, by brittleness, and we like the things to be flat and even in the page. So, like any collectible or rare item, the condition of a potentially valuable comic book is all important. The condition is we maintain it with proper storage, right, Rufus? We use these backing boards to keep there from being wrinkles, or this is the shape of it. And we use things like these bags, Mylar or polypropylene most often, to keep contaminants away from the surface of the book, which actually aren't all that great sometimes because they also keep the acid from evaporating away. So there's that. But over a period of time, though, comic books are inherently unstable, especially older books, because they weren't meant to be preserved, and they will gradually turn yellow, or rapidly turn yellow if they're exposed to sunlight and moisture, of course. They'll turn brown or even brittle. And needless to say, none of us wants our comic books to gradually turn into dust. The danger is from acids in paper, and I'll explain that a little bit more in the future here. It's not just unique to collectors of comic books, but it's a big problem in a nation's libraries in general in the United States and in other countries. In fact, I sometimes am sent documents from the British Virgin Islands because they have so many hurricanes and other storms there to kill and remove mold and to try to preserve and archive papers there. Now that it used to be formerly that the National Archives here in the United States can preserve documents, and that's another story. It has been estimated that of the 90 million books in the Library of Congress, approximately 30% of the total are too brittle to put on a scanner and scan, because there's a fear that the paper may break or otherwise be damaged. So that's a lot. A recent study in Yale University found that 37.1% of the books sampled had brittle paper, and 82.6% of the books there had acid paper with a pH of 5.0 or lower, which means that they're going to decay rapidly. So book deterioration and document deterioration is a serious problem, even though these days a lot of that stuff is done electronically. The bulk of the world's paper records are aging. So we're going to talk today about in the next few episodes, about the acidity of pulp paper, and it's found in comic books and library collections, and we're going to talk about the various factors that contribute to the deterioration of this paper, which we'll think about preserving them from a chemical perspective, because I'm a chemist. We're going to first talk about acid catalyzed hydrolysis of the cellulose. We're going to talk about the effect of temperature. We're going to talk about the effect of light. We're going to talk about the effect of acidity, maybe moisture, but we will talk about the effect of oxygen and oxidation. And then in the future, once we have this baseline, we'll use this information to talk more about other things like foxing and sizing and ink seepage and other ways to preserve stuff. So anyway, I hope you enjoy this episode, and we'll have more in the future. Okay, hang on there for more. Right, Rue? Good boy. I know. They're all excited. I can tell. So forgive me if this is more podcasty than anything. So I'm going to leave some pictures up here while I just talk and read you some of my notes. So, like any collectibles and rare items, the condition of a comic book is all important. It's something we all talk about and we obsess over, and some people just got to have 9.8 this or 9.6 that. And part of that condition is the paper itself, of course. This condition is maintained by proper storage and what we call permanent deacidification. One of the underlying reasons for the inherent instability of comic books is the presence of acids found in the pulp paper in general. Thus, over a period of time, a comic book with white pages will, as we've all seen, gradually turn yellow, or in fact rapidly if continuously exposed to sunlight and the elements, and may even eventually turn brown and brittle. No collector wants to see their collection, valuable or not, turn slowly into dust. And this is why we have comic book bags and boards and things like that. The danger of acids in paper is not unique to collectors of comic books, of course, but it is part of a more general problem also faced by libraries. I, in fact, have dealt with people in the British Virgin Islands who had a problem with mold from all the storms they get in hurricanes down there, and their books are also turning brittle. It's not so much of a problem with new documents, but it's been estimated that a third of the 19 million books in the Library of Congress are too brittle to even be scanned, that they would just break apart. So it's pretty bad. It has been estimated a large-scale university book deterioration study at Yale has provided some statistics to support these estimates. It has been found that 37% of the books sampled overall at Yale had brittle paper, while 86% of the books had acid paper with pH below 5.4, which is pretty low for books. So what's going on in paper? This is what a paper repeating unit looks like. It's called we know that the acid catalyzed hydrolysis of cellulose in paper fibers has been established. It's the main cause of paper deterioration in library books, and the statement can be made for comic books too, made of pulp paper, which is all comic books. It's especially true in older, especially Silver Age books. The structure of cellulose has been described in my article here, and I've even done some FTIR and NMR studies myself, and it shows that it's this 1,4, we call it 1,4 beta glycosidic bonds, which is this one here, this 1 to 4 beta glycosidic repeating unit. This is a repeating unit. This is a chain. This that you see here, whoops, I don't mean to move that, is a chain. These things, these units here, this is a dimer, we call it a two-member chain, this gets repeated, and it goes like this over and over. There's these two units. That's called a polymer when we see that. This is called a polymer. And it's a polymer link of dimers. Now, if you take another polymer and you put it this way, and then you put links between them, which we have in paper, that's called cross-linking. Cross-linking. In this case, it's something we call, don't worry about what it is now, but it's what that is specifically, but it's called hydrogen bonds. Hydrogen bonds cross-link the polymers, and this gives it rigidity. This is what makes the paper rigid, is this way, and strong, meaning won't tear easily. Strong is this way. So if you have a long lefty-righty, you're strong. You have lots of upsy-downy, you're rigid. And just think that the getting paper wet will actually sort of break these, it softens these hydrogen bonds because they want to go to water more than they want to cross-link. And that makes the book floppy when you get it wet. But when you remove the water, you can bring that back. But it's easy to tear when it's not cross-linked. Of course, it tears along the hydrogen bonds, not necessarily along the polymers. So that is called the crystalline portion. So if you see something like that in paper, we say that this is crystalline in nature. And I just told you some properties that we can measure from the crystalline part. There's also parts of it they're like this, that's called the amorphous. This is the amorphous. It's kind of like the boogers and goo. It's from lignin and other stuff that are in the paper too. So this ratio of crystalline versus amorphous portions of the paper are what give it its properties. The water, and since acid is water soluble, the acid are in the amorphous part. That's where that stuff lives. So you have this combination of crystals and amorphous and crystals and amorphous, and that's what paper is made out of. And those are the things that we're battling here in paper. We measure this stuff. We call it the degree of polymerization. In a tree, normal tree wood, we have this thing called the DP, the degree of polymerization, and that's about 1,000 in a tree, and it's about 100 in regular paper cellulose. Drops to about 400 or 200 when the paper has been aged. And this is called beta-linked anhydroglucose units, which are been broken, and that's where we lose our strength. I hope that makes some sense. So again, if we were to look at this, we would say that if something had a very, very long, a very, very long chain, it is very strong. And if it has, but it might be flexible, but it's strong. Meaning strong meaning you can't tear it apart. If it has a very short chain, it would be brittle. Now, you can be strong and not very rigid, meaning that you're kind of floppy because it's just like a rubber band, kind of, right? So if you were to add some cross-linking here, this is what makes it rigid. And the cross-linking is from hydrogen bonds, and the polymer length is what gives it this rigidity. There is a metric that we use called DP, or degree of polymerization. So this is called DP. I'll get a bigger pen here. It's called DP, degree of polymerization. If the degree of polymerization is large, then it's strong. So in a tree is wood paper pulp is about 10, has a DP of about 10,000. Normal during the manufacture of paper, the DP of cellulose drops to about 1,000. So it's about 1,000. So it goes from there to about 1,000. The presence of acid in paper can catalyze the hydrolysis of the cellulose. So that's this guy right here. It catalyzes that so that the DP can drop to, it's often around 400 to 500. The page becomes brittle, and it starts to look yellow too because there's some color. We call it chromophoric. There's a color associated with this. So the amorphous regions of the paper. Now remember before I said that I mentioned that there are both crystalline and amorphous regions. Well, all the water and therefore the acid are stored up in these amorphous regions of the paper, the non-shapy stuff. And they are the ones, the amorphous regions of the cellulose that contain water are penetrated by acid. The DP tends to level off about 200 because all of those amorphous regions, the goo, right? This contains all of the acid and the water, and that stuff tends to pump this stuff into the rest of it, and it runs out. Depending on how much of the amorphous regions you have, they sort of get depleted over time initially. Now that can be propagated, and I'll tell you about how recently in a minute. But once those run out, the DP tends to level off around 200 before the paper turns to dust. That's where we see things sort of level off naturally in comic books. And so, but by the time it gets there, it's really brittle. It's super brittle, and you see the pages get like stiff, and that's what we call this. We sometimes call this marvel chipping, especially on the outside and the cover. The cover of a book is where we notice this most often. We see it the most because it gets the most bending typically, or it's the most abuse. But marvel chipping has a DP of around 200. We are all familiar with this, especially in the old Silver Age books, and that is what that is called. So one of the questions is, what if you put more acid in it? Is stuff going to get worse naturally? Well, further attack by acids on the remaining crystalline cellulose structure is not likely to continue after about 200 unless the paper were directly exposed to acid itself, like you put some acid on it. Under this extreme condition, the hydrolysis of cellulose can produce disaccharide. We call it cellulobiose, and we can even, if we put some strong hydrochloric acid on it, it produces D-glucose. It makes sugar. 75. I mean, you can take 95% of the stuff and literally make sugar out of it when you completely destroy the 1,4 beta-glycosidic linkages entirely. So that's kind of cool, really. But the mechanism for acid catalyzed hydrolysis. Now remember, the acid's not really doing any of this stuff. Catalysis means, what does that mean? Catalysis is something that makes a reaction happen but doesn't get consumed or really participate in the reaction itself. There's lots of examples like this, and your catalytic converter doesn't get burned up. It just helps you to reduce your emissions. So the first step in this mechanism is a rapid proton. Now a proton, it means acid, in case you don't know that. It's a rapid proton attack of the oxygen atom in the 1,4 beta-glucosidic linkage. So if you look here, that's what I'm trying to show you is that, let's see if I have a picture over here. Well, this is a picture of just the glucose chain being broken here. This is called hydrolysis. So this is plus water here. You lose water in the presence of acid. That's what this means. When you see this little symbol above an arrow, it means in the presence of the acid is not consumed. It breaks this chain and it becomes shorter. So that's what's happening. However, when you have acid attack, this is acid here. This is called a proton, and it's what defines an acid as being an acid. We have this other group here called a hydroxyl group, which defines things as being a base. So if you have acid attack, the presence of acid in the paper causes this we call it hydrolysis. It breaks it right here. Okay, it breaks this apart. Now, the interesting part about it is that this involves a rapid, really fast proton attack of the oxygen atom here that you see. In the second, now this is the slower step. This is fast. This is very, very fast. This is what we're going to study kinetics later. This is slow. This is the rate determining step. This tells you how fast your paper is going to age in this process, because everything can only go as fast as this part happens, not the proton attack, which is fast. Now, the shift of the electron pair between the acetal oxygen atoms results in the rupture of the cellulose chain. So what does that mean? That means that this hydrogen stuck here, this little guy stuck on that guy, and this transfer of this electron, which is normally in a bond, goes to this oxygen here in the middle. That is the slowest part of it. We call this the heterolysis. So This heterolysis produces an intermediate carbonium atom. Now, what does carbonium atom mean? Carbonium atom means this guy. This is called carbonium. It means a positively charged carbon, C+, in a chain. That's called carbonium. It produces a carbonium cation and a water molecule. And a water molecule will the reaction between this carbonium cation and a water molecule, that's because there's water. Where's this water come from? It's like, hey man, where's this water coming from? Well, the water is from the amorphous parts of the paper, or just from the atmosphere. It's just humid. So that's the source of the water here. So the reaction between the carbonium cation and a water molecule results in the formation of a neutral group, N group. So what happens here? Oh, it's just neutral. It forms, this is just neutral. Oops. I don't know why I erased it here. See? This isn't meaning no charge. It's no plusy minusy. Okay, that's a neutral form. But here's the thing. Plus a proton. So it's a neutral group plus a proton, which goes on to destroy more paper. Get it? So it results in the formation of a neutral N group and the regeneration of the acid proton. This acid catalyzed depolymerization of the cellulose chain, which can occur over and over again, is the major cause of the deterioration of paper and aging in comic books. So this whole process, like, let me sort of go over this again a little bit here, just so that you can see what's happening, is that you're just minding your own business. And the catalysis, and this is called catalysis with acid, happens mostly in the presence of acid. It happens that this comes up here, this forms this way, it leaves a plus on the other side. The water comes in here and neutralizes that, but in the process it leaves this off to go do another one, and this is where the chains break and they're becoming shorter, and this is the embrittlement part of it. Now we're going to talk now, this is helpful because if you don't have any acid and you don't have any water, none of these things can happen, right? So we're not seeing that effect. Now, next we're going to talk about the sources of acidity in paper. We're going to talk about the effect of temperature. Then we're going to talk about the effect of oxygen and the effect of light, and what we can do to stop this from happening, as reversing it is nearly impossible. But that's where we'll go next. I hope you have enjoyed this video. Take care. Bye-bye.